Proxima Centauri, the closest star to our solar system, has long been a subject of fascination for astronomers. This small red dwarf, discovered in 1915 by Scottish astronomer Robert Innes, is part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its proximity just 4.24 light-years away, it remains invisible to the naked eye due to its relatively low brightness. However, Proxima Centauri holds immense scientific value, especially as the host star of Proxima B, an exoplanet that orbits within the star's habitable zone. Red dwarfs like Proxima Centauri are smaller, cooler, and much longer-lived than stars like our Sun. Their low luminosity makes them challenging to observe, but it also means that their habitable zones are much closer to the star for Proxima and Tauri. This translates to an orbital distance of just 0.05 astronomical units, a mere fraction of the distance between Earth and the Sun. This close proximity exposes Proxima B to intense stellar activity, including frequent solar flares and high levels of radiation, making its environment starkly different from Earth's. The discovery of Proxima B was a monumental achievement in exoplanet research. Using the radial velocity method, astronomers detected subtle wobbles in Proximus Anders' position caused by the gravitational pull of an orbiting planet. These wobbles allowed scientists to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the existence of Proxima B, marking a breakthrough in the search for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights into Proxima B, they come with significant limitations. Atmospheric distortion and light interference hinder the ability of Earth-based telescopes to capture detailed data about the planet's surface or atmosphere. Most of the information we have, such as its mass, distance from the star, and orbital characteristics, relies on indirect measurements to uncover deeper truths about Proxima B's environment and its potential for life. More advanced observational tools like the James Webb Space Telescope (JWST) are indispensable. Proxima Anders' role as a gateway to understanding exoplanetary systems cannot be overstated. As the closest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima B in particular represents a tantalizing possibility, a rocky, Earth-sized planet with the potential to harbor water and maybe even life. However, the challenges posed by its harsh environment make it a complex puzzle for scientists to solve. The James Webb Space Telescope (JWST) is not just another tool in the arsenal of astronomy, it is a revolution. Designed as the successor to the Hubble Space Telescope, JWST was envisioned to address the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided invaluable insights into the cosmos, its capabilities are constrained by its focus on visible and ultraviolet light. JWST, in contrast, is built to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust and uncover phenomena invisible to Hubble. One of the key design features of JWST is its primary mirror, which spans a staggering 6.5 m in diameter, more than double the size of Hubble's mirror. This larger mirror enables JWST to collect far more light, making it capable of observing extremely faint and distant objects coated with a thin layer of gold to enhance its infrared reflectivity. The mirror is composed of 18 hexagonal segments that work together to create a highly sensitive observational platform. Another groundbreaking innovation is JWST-F layer sunshield, which keeps the telescope's instruments at a constant temperature of about 233 degrees Celsius. This ultra-cold environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second range point L2, a stable position, approximately 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. The telescope can study everything from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its focus on infrared light is particularly significant as it allows astronomers to study phenomena that are redshifted objects whose light has been stretched to longer wavelengths. As the universe expands, JWST capabilities extend far beyond mere observation. It is designed to answer some of the most profound questions in science, including the origins of galaxies, the formation of stars, and the conditions that might support life on other planets. With its state-of-the-art instruments, including the near-infrared camera and IR-CAM, the infrared instrument MIRI, and the near-infrared spectrograph NIR, JWST is not just a telescope, it is a time machine, a laboratory, and a beacon of human ingenuity. Proxima B has captivated scientists and the public alike as a potential second Earth. Situated within the habitable zone of its star, the planet has the right conditions to potentially support liquid water, a key ingredient for life as we know it. With a mass roughly 1.17 times that of Earth, Proxima B is likely a rocky planet similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima B is far from a perfect twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual daylight while the other is in eternal darkness. This creates a unique environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, may offer a narrow twilight zone with conditions moderate enough to support life. The challenges posed by Proxima B's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can emit bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima B retains any atmosphere, it likely requires a strong magnetic field to shield it from radiation. Without such protection, the surface and environment would be hostile to life as we know it. Despite these challenges, scientists are optimistic about the potential for life on Proxima B. The planet's position within the habitable zone suggests that liquid water could exist either on its surface or in subsurface reservoirs. Life might adapt to the harsh conditions, much like extremophiles on Earth. Organisms that thrive in extreme environments such as deep-sea hydrothermal vents or high radiation zones. These adaptations could include radiation resistance, subsurface habitats, or unique biochemical processes. The search for life on Proxima B is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions: are we alone in the universe? Proxima B represents a tantalizing possibility, a rocky Earth-like world that might harbor the conditions necessary for life. As our technology advances, so too does our ability to explore this intriguing planet and uncover its secrets. While Proxima B presents tantalizing possibilities, its environment is profoundly influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf star, smaller, cooler, and significantly less luminous. Its reduced size and temperature mean that its habitable zone is much closer, pulling Proxima B into an orbit just 0.05 astronomical units from the star, about 20 times closer than Earth is to the Sun. This proximity creates a unique set of challenges for the planet and any potential life it might host. One major issue is Proxima Centauri stellar activity, particularly its intense and frequent solar flares. These flares are sudden, powerful eruptions of energy that release high doses of X-rays and ultraviolet radiation. Such events are far more common and energetic in red dwarfs than in stars like our Sun. For Proxima B, this means a constant bombardment of high-energy particles, which could strip away the planet's atmosphere over time without a protective magnetic field. Any atmosphere on Proxima B would be vulnerable to erosion, leaving its surface exposed to harsh radiation. Even if Proxima B retains some of its atmosphere, the radiation from Proxima Centauri poses serious challenges to life. High levels of ultraviolet radiation can break molecular bonds, preventing the formation of complex organic compounds. This would severely limit the potential for life to develop or sustain itself on the planet's surface. On Earth, organisms like Deinococcus radiodurans have evolved mechanisms to repair DNA damage caused by radiation, suggesting that life on Proxima B might similarly adapt. However, the level of radiation resistance required would be extreme, possibly necessitating entirely new biochemistries. Interestingly, Proxima B's tidally locked nature may offer some protection. While one hemisphere faces constant radiation from Proxima Centauri, the planet's dark side could serve as a refuge. Subsurface habitats or deep caves could shield potential life forms from the worst of the radiation. Similarly, if Proxima B has subsurface oceans, they could provide a stable radiation-free environment where microbial life might thrive, much like the ecosystems around hydrothermal vents on Earth. Despite these challenges, scientists remain hopeful that Prox B's extreme environment provides a unique opportunity to study the adaptability of life by observing how organisms might survive or even thrive under such conditions. Researchers can expand their understanding of what makes a planet habitable. Proxima B is not just a potential home for life, it is a natural laboratory for testing the limits of life itself. The planet's proximity to Earth and its position within the habitable zone of its star make it an ideal candidate for further study. With new telescopes and instruments, scientists will continue to monitor Proxima B for signs of habitability and life. While Proxima B may not resemble Earth in every way, it offers a tantalizing glimpse into the possibilities of life beyond our world. Its discovery raises important questions about the nature of habitability and the resilience of life in the universe. As technology advances, we may one day find evidence of life on Proxima, or at the very least learn more about the complex conditions required for life to emerge in distant worlds. Until then, the search for life on Proxima B continues to captivate the imagination of scientists and the public alike. The study of Proxima Centauri and its exoplanet Proxima B is central to the growing field of astrobiology, which investigates the potential for life beyond Earth. Over the years, research has highlighted several aspects of this distant system that make it a prime target for ongoing investigations. For one, red dwarf stars like Proxima Centauri are the most common type of star in the galaxy, meaning that understanding systems like Proximus and Tauri could provide valuable insights into a vast number of other star systems, as red dwarfs have lifespans many times longer than that of stars like our Sun. Proxima Centauri is expected to remain active for billions of years longer, offering a stable environment for any potential planets within its habitable zone. This extended duration allows for the possibility of life evolving over long periods, potentially leading to more complex forms of life that could withstand the harsh conditions imposed by its parent star. In fact, red dwarfs like Proxima Centauri could potentially host multiple Earth-like planets in their habitable zones, opening up the intriguing possibility that such systems could harbor not one but several habitable worlds. One of the questions surrounding Proxima B is whether it has developed an atmosphere capable of protecting life without a magnetic field. The planet could face the erosion of any atmosphere by the intense stellar flares from its host star. However, new research suggests that if Proxima has a thick atmosphere, or if it has an active geologic history that could create a planetary magnetic field, it might still have a chance at retaining an atmosphere for long enough to support life. In fact, scientists have theorized that life on planets orbiting red dwarfs might be significantly more resilient to radiation than on Earth, evolving mechanisms to cope with high levels of radiation and extreme environmental conditions. The process of planetary evolution also plays a significant role in determining whether Proxima B could be habitable. If the planet has experienced volcanic activity or plate tectonics, these processes could contribute to a stable climate by recycling carbon and regulating surface temperatures. Such geodynamic activity would also be crucial in replenishing the atmosphere, ensuring it remains thick enough to maintain liquid water even under the influence of solar flares. These possibilities make Proxima B an even more exciting prospect for future exploration. Despite its challenges, Proxima B is an ideal candidate for the next generation of space telescopes. Instruments like JWST and the upcoming Extremely Large Telescope ELT in Chile could play key roles in analyzing the planet's atmosphere and looking for bio-signatures, signs that life could exist or has existed on the planet. Spectroscopic analysis of OAB atmosphere could reveal chemical signatures such as oxygen, methane, or carbon dioxide, which would be potential indicators of life. JWST ability to observe an infrared could also allow for better analysis of the planet's surface temperature, weather patterns, and any seasonal variations, potentially providing clues about the planet's climate system. If Proxima B were to be confirmed as habitable, it could transform our understanding of where life might exist in the universe. The search for life beyond Earth is not limited to finding Earth-like planets orbiting Sun-like stars. Instead, researchers are broadening their focus to include red dwarf stars. Many of these stars, including Proxima Centauri, are older and cooler than our Sun, providing an environment where life might adapt in unique ways. Moreover, red dwarfs are abundant, with some estimates suggesting that as many as 70% of stars in the Milky Way could be red dwarfs. As such, Proxima Centauri is just one of many systems that could harbor planets in their habitable zones, further emphasizing the importance of exploring red dwarf star systems.